All right, to everyone. So I've chosen a somewhat deliberately scary title. I promise it's not that bad. Go through it all and hopefully you understand everything by the end. So to start with, why are hydrodynamics important in astrophysics? We know that many sources in astrophysics that we study are fluids or involve fluids in some way. And these are generally complicated things to model or study. They don't have analytical solutions. So we ask ourselves, how do we model these things? And one way we do this is computational fluid dynamics. So, the next natural thing you want to ask yourself, well, what about relativistic sources, relativist fluids? So, either consider fluids moving at relativistic speeds, jets, we've got M87 there, or a fluid moving in the presence of a strong gravitational field, like a black hole accretion. And the answer is, well, we solve the relativistic fluid equations. We do this numerically. And typically, we do this by solving it on a grid. Have your conservation of the stress energy tensor and your conservation of the time density. We can do this provided we have an analytical solution for our metric. But as I hope all of you know, that there aren't that many solutions to the Einstein field equations analytically. So how do we go about solving this? Okay, so the answer is numerical relativity. The idea behind numerical relativity is you split your space into space-time, I should say, into space and time slices. I like to think of this numerical relativity textbook. So I like to think of this as splitting your space-time into sheets of space, which you then integrate with time. So you can imagine each page in the book is your space, and you solve the space for that page, and then move on to the next page. So this is something that's quite used in a simulation of black hole binaries. Now we have LIGO, lots of LIGO sources. We use this to get gravitational waves. Yeah, I'm not going to talk about NR too much. It's a very, very complicated field. Many equations. There's that textbook there if you're interested. I can also come and talk to me and I can point you towards some papers. I'll try and keep the equations to the minimum, but I'll give you a little taste of how bad we can get. Okay, so relativistic hydrodynamics and numerical relativity. We have some fluid that's moving and we want to solve for its metric. So the way we do this is we use numerical relativity. We have the Einstein field equations. We solve the metric numerically using numerical relativity. And then we calculate a stress energy tensor for our fluid using computational fluid dynamics. Okay, I spoke about this briefly before, but why do we want to do this? The main reason is involving neutron stars. A bunch of different neutron star simulations, a neutron star black hole, neutron stars with magnetic fields, gravitational wave extraction in neutron star. So that's great. There are a few issues to doing this, on a grid at least. The first one is vacuum spacetimes with math. So what do I mean by this? When you imagine you have a neutron star, you have this very, very dense material, and then suddenly you go to a vacuum. So this is something that can't be done on a grid. You can't have a pressureless vacuum. You have to embed it in an atmosphere. And this leads to some problems with trying to get things as accurate a problem. Another issue is the ejection of material. I showed before some neutron star merger simulations. What happens is you get a large ejector of material. And if you try and do this on the grid, all of your resolution is concentrated near the neutron star surfaces, and you can't track it to large distances. which is important for electromagnetic follow-ups of gravitational wave sources. All right. What I'm going to be talking about for the rest of this talk is inhomogeneous cosmology. So this is another application of numerical relativity. I hope most people are familiar with standard Newtonian cosmology, I'm going to call it. This is sort of similar, but rather than just solving the Friedman equations and using that for your expansion, you instead calculate the expansion of the universe using numerical relativity, so full GR. And this has been suggested as a possible explanation of dark energy. I'm not going to go into that. So basically speaking, here we have this is a fancy Friedman FLRW metric with extra terms that come from relativity. So vector term, relativistic potential, and there's what you call a gravitational wave. So a bunch of people have performed simulations using numerical relativity. There's a bunch of them here. A few approximations to GR that are worth mentioning. We'll talk about them later if you're interested. But they all have one main problem. And this is a shell crossing. So I want you to imagine a sheet of matter. What happens is, I've got your picture up there. There's a picture there. What happens is your velocity becomes double valued and your density shifts to infinity at the point of shell crossing. And what this means is your code crashes. Try and do this on a grid, your code crashes. So all of these codes, back a second, either approximate this or treat this in a special way. So the question we want to ask ourselves is, well, if we treat this in a special way, we can't have structure formation. I've got a picture here from the other SPH code that won't be named. The millennia run, I hope everyone's seen this. Haven't. Basically, what we have is we have a cosmic structure formation, and hopefully you can see these little spheres or ellipses, and these are your dark matter halos. So if we want to do full structure formation with numerical relativity, we can't. This is just a slide to illustrate the difference. Hopefully it comes out well. Okay, so what's the solution? Well, the solution is to use particles for the hydrodynamics. So I think everyone in this room hopefully understands the Lagrangian formalism. If you don't, instead of looking at grid cells, imagine that you're a boat moving down the river with the fluid. So this is what I propose to do. So how am I actually doing this? I'm using two codes. The first is the Einstein Toolkit, which is a publicly available numerical relativity framework, and it solves the Einstein field equations using something known as the BSSM formalism. It has support for a lot of physics. As I mentioned before, binary black holes, binary neutron stars, neutron star black holes. It also has support for initial conditions for inhomogeneous cosmology, provided by Thorne, known as FLRW solver. Right, so the second code, which is why I'm talking to you today, is phantom. I don't think I need to cover this too much. The main thing that I want to talk about is we have support for general relativistic hydrodynamics for any fixed metric currently. So we've heard some great talks from TDEs. I have another talk by Fitz after me. It's also being used for neutron star black holes, just to illustrate some of the potential applications so far. All right, so on to what I'm actually doing. The basic idea, as I mentioned before, is to split the metric evolution and the hydrodynamic evolution between two codes. So the grid code, Einstein Toolkit, handles the metric evolution, and the hydrodynamic evolution is handled by Packer. So in order to do this, I need to get some metric quantities, in this case the metrics themselves and the metric derivatives, onto the particles in Packer. So I do this by interpolating, and then after the interpolation we can evolve the equations of hydrodynamics in phantom, and then finally we can calculate a stress energy tensor, and then finally we can interpolate these quantities back to the numerical relativity code and evolve our metric. All right, it's all very well and good for me to stand up here and tell you that this doesn't actually work. So I want you to consider a really, really boring universe, essentially a flat, constant density box. It's dark matter, which means it's pressureless. There's no dark energy. So this is very nice because this means I can solve the Friedmann equations and compare them and get some analytical solutions to compare to. So have an evolution of the scale factor and density. So basically what happens is what you'd expect. Your universe expands, your scale factor gets bigger, and the density decreases. So the more important result is shell crossings. So as I mentioned before, generally when you try and do this, you get to a point where your velocity becomes double valued, your density shoots to infinity, and your code crashes. So I have the initial conditions here on the left, and on the right I have a snapshot from phantom evolved to world-class shell crossings. So what I want you to get from this is this means we can do proper structure formation in numerical relativity. Just for fun, this is the same thing in 3D. Same as this plot. So we start with a sinusoidal perturbation in all directions, and then it collapses. And then shell crosses. All right, to sum up. Particle-based hydrodynamics provides a solution for shell crossing singularities in NR. This is the biggest takeaway from this talk. What I want to say to you is that it is possible to do realistic structure formation in inhomogeneous cosmology. And another thing which I briefly touched on is simulation of compact object mergers. We can easily extend this to binary neutron star mergers or neutron star black hole mergers. Thank you very much.
Thank you for the great talk, Spencer. Does anyone have any questions?
Hello, very great talk, great work. Just a curiosity, so when can we use this code with dynamical evolution?
When?
Yes.
Oh, I don't want to give a timeline because I set myself up for
I don't want to put pressure on you, but it will be great as soon as you can. I mean, this will be actually great. I mean, it's like having a code with Phantom that simulate fluid dynamics so well. With numerical relativity implemented, basically, it will be amazing. So please update me when, as soon as it is available. I want to know.
Yeah, amazing talk. I'm surprised, the amount of numerical terms that you have to solve. But my question is regarding the time stepping.
Okay. So, are you curious about the integration or the?
A little bit, because it's like I mean, in Newtonian regular, when we try to apply individual time stepping, which I think will be something that you kind of have to do in this case, or maybe not. I don't know.
So, I spent a significant portion of my life trying to get string splitting working. The simplest thing to do was just use RK4. Yeah. You can write it as a method of lines version, so you just have a right-hand side, and it's all very simple. It's all handled by Einstein Toolkit.
Oh, okay.
Yeah, silly question. Have you tried with a non-boring universe? Like you said, like with the boring universe, you had like the right
So-
rate of expansion and everything, but just out of curiosity, have you tried?
Like a full Gaussian perturbation?
Yeah, something a bit more sophisticated. I mean, do you think it will be possible and you would?
It's definitely possible. I'm at the stage now where these shell crossings, where this is kind of the proof of concept that you can actually do those large scale simulations that you're talking about. So I'm not quite at the stage of production runs yet because optimization and things like that. But in terms of initial conditions, it can definitely be set up and done.
And how long does it take? Like these kind of simulations, like do they run for like weeks, months, years?
Yeah, well, I haven't done the scaling tests to tell you honestly, but longer than a regular Newtonian code.
And if I could just ask a possibly stupid question, what's the cosmological motivation for having a perturbation as an initial condition?
In this one?
Well, just having like a not flat initial condition.
Oh, okay. So this comes from, I don't have a slide of this. Imagine you have your inhomogeneities, your small inhomogeneities in the cosmic microwave background. And this is, at least when you simulate things, what gives you your little fluctuations. And then these little fluctuations are what lead to your structure formation.
Okay, thank you. Unless there are any more questions, we'll move on to Fitz, who's online. Thank you, Spencer, once again.